Hello! Welcome to Science and Hypotheses. In this video, we'll address the question, what is science? We'll consider some criteria that guide science rather than considering a definition of science, which is something we've done in a prior video. To help motivate today's conversation, when we address the criteria that guide science, we'll use some examples that relate to Charles Darwin's theory of evolution. We can begin by asking whether a Darwinian explanation for a given psychological phenomena satisfies the criterion of falsifiability. Falsifiability addresses the issue of the extent to which a claim is testable. And this word, falsifiability, confuses some students. They erroneously believe it means the same thing as being false. But there's a distinction between something being false, which is to say that thing is untrue or that claim is untrue, versus something is falsifiable, which is to say that the claim is testable. That is, you and I could run an experiment or make some observations that would, in principle, show that the claim is untrue. So falsifiability is one of several criteria that we could use. Here's a second criteria that we could use if we're guided by science, and this is the criterion of replicability. Can a test be redone at will? It's very important that psychologists and other scientists can take an observation or an experiment and redo that experiment and get at least approximately the same kinds of outcomes. And to the extent that we can replicate earlier findings or earlier observations, we tend to have confidence in the claim that's being made about a given phenomenon. Another criterion that guides a lot of science is the criterion of parsimony. And this is the issue of whether there are unnecessary or unnatural components in an explanation. Generally speaking, psychologists and other scientists prefer explanations that are parsimonious. That is, they don't contain any sort of unnecessary component to them. They're as straightforward as they can be. There's a related idea here that some of you might know from a philosophy class. And this is the idea of Occam's razor, which states that all else equal, the simplest explanation is preferred. Now, the three criteria that we're showing here are not the only criteria that guide science, but these are frequently occurring criteria, and it was important to mention them here because they occur so frequently when we're thinking about science. Of course, all of these are ways of evaluating hypotheses. So let's talk a little bit about hypotheses. First, we'll start with a definition. We can define a hypothesis as a testable and tentative explanation for a phenomenon. And there are lots of different phenomena that we might consider as psychologists. For example, it might be that a social psychologist is interested in the idea of physical attractiveness. And the social psychologist might invoke a Darwinian explanation for physical attractiveness. It might be that a different psychologist is interested in intelligence. Maybe this is a cognitive psychologist who's interested in Darwinian explanations of intelligence. Maybe a clinical psychologist is interested in a totally different phenomena. It might be depression. And we can think about Darwinian explanations for depression. In all cases, though, any of the hypotheses would be testable and tentative explanations for a given phenomenon. Importantly, science does not prove hypotheses, and this is something, too, that confuses a lot of students. In everyday life, you'll hear people make claims like, oh, scientists have proven X or Y or Z. But that's actually incorrect. Science does not prove hypotheses. Prove is too strong a word. Scientists do reserve the word prove for mathematical proofs, but not for issues of empirical investigation. That is to say, if we're collecting data on, say, psychological phenomena, maybe physical attractiveness or intelligence or depression, we might find data that are consistent with a particular hypothesis, but don't prove a hypothesis. So in our course in psychology, we hope that you will remove prove from your vocabulary. We reserve prove only for mathematical proofs. Otherwise, the use of the word prove is simply too strong for the claims that scientists typically make. So what do we use then? We instead use this terminology. Science either rejects or disconfirms a hypothesis or fails to reject a hypothesis. So we don't say that we prove it, we say that we either reject or fail to reject. And there's a lot of caution there. And the caution speaks to the scientific rigor. Science is a relatively rigorous way of knowing, and scientific conclusions and scientific hypotheses demand evidence. strong claims demand stronger evidence. So for example, let's return to the issue of depression. And you can imagine that somebody might have an explanation, a tentative explanation for depression. We would call that a hypothesis. The hypothesis might be Darwinian, and we can evaluate it on lots of different criteria, but we would demand stronger evidence for stronger claims about depression. So for example, it might be that somebody claims that they can explain all kinds of depression. Well, that would demand a lot more evidence than somebody who's claiming only that they can explain depression of a particular variety in a particular sample. I mean, that would be a less strong claim. It would not demand the strong evidence that a stronger claim would demand. Scientists also seek to challenge their own hypotheses. They're very open to the possibility that they've been wrong about a hypothesis that they've been investigating, and it's really about the evaluation of hypotheses, not an evaluation of the scientist himself or herself. Scientists must allow others the chance to evaluate, replicate, and reinterpret the findings using the scientific method. So we're very open to lots of different possibilities when we're evaluating claims, and this is part of scientific rigor. Finally, scientific conclusions typically rely on multiple studies. We call these converging studies, and it's even better when we have diverse methods yielding similar kinds of conclusions. Sometimes we'll see a seminal study or a seminal investigation. That's a novel investigation of a new topic, and that might be promising, but usually scientists are very cautious in interpreting too much from a single study. A multitude of studies would provide stronger evidence. Finally, we'll close with this idea. Science is also very practical, and science can provide information. We can think of information as the reduction of uncertainty, and I hope you'll jot that down. Information is the reduction of uncertainty, and we can reduce uncertainty in a broad variety of practical settings. For example, settings that relate to parenting or teaching or athletics, art, medicine, civic activities, politics, everyday life. Science is broadly practical, has many everyday applications. Thanks for watching.